your blood pressure, the chemokine system, which is very important for inflammation. Now, we've studied this and found that if you want to completely block the signaling from those two pathways because they form a complex, you actually have to treat with two drugs. You have to block both of them in combination. So this is for what's called arrestin binding, but more interestingly is a signaling protein that is used for the chemokine receptor, which is GI. GI signals through the chemokine receptor and gives the inflammatory response. But very interestingly is the arrestin molecule and the arrestin receptor actually can affect this inflammatory process. So if you activate the angiotensin receptor, you can inhibit the inflammation. Now, why is that important? Well, for chronic kidney disease, for example, most of us treat patients with an angiotensin blocker. So you're blocking the angiotensin system. But unfortunately, that could actually be unmasking an inflammatory response. So from this, we got the idea that it would be a good idea to treat with a combination of two drugs, one against the angiotensin receptor and one against the chemokine receptor. So inflammatory kidney disease. The major endpoint of this is having protein in your urine, which is very bad, so we call this proteinuria. And in an animal model here, we can see that not just blocking the angiotensin, which is the treatment we give to patients, but additionally blocking the chemokine with something called propogermanium means that we can now give a much better response. So this worked very nicely in the rats. You can see that you can improve the macrophage number and also improve the cell that we believe this is working, which is called the podocytes in the kidney. So that worked very nicely in rats. And then moving on, we've taken this through into clinical trial. So we just had a very successful phase 2A clinical trial, 27 patients in 4 sites across Australia. These patients were on the standard of care, which is irbesartan, for at least 3 months. And then we added an additional dose of propogermanium to block the chemokine receptor. We found the primary endpoint was safety and tolerability, and the secondary endpoint was efficacy. And the results from that were the compounds were safe, no serious side effects. 6 of the 24 patients that finished the trial had a greater than 50% reduction. So irbesartan reduces that response to about 25%, so reduces the proteinuria to about 25%, and then additionally, we brought that down another 50%. So a massive response, very clinically important. So that trial data is now informing us on a phase 2B trial, and very importantly, 11 of those patients applied and were granted access to continue the treatment because this treatment is not available currently in Australia. They had to get special access permission, and that was granted. So 11 of those patients continued. So in summary, we have a proprietary receptor hit technology. We have intellectual property around this. It enables identification and profiling of heteromerization for drug discovery. Can be applied to a wide range of receptor systems. I mentioned 3 indications we're interested in, but we've looked at others as well, such as neuroscience. We have granted IP, both in terms of the platform, but also in terms of the adjunct therapy. We have successful research collaborations with multiple biotechs. We've had some very good collaborations with Takeda and another 2 of the top 10. Unfortunately, I can't tell you who they are, but you can probably guess their names. And we can leverage this entire profiling capability for looking at receptor function. And then finally, before Andrew steps on the stage, I'd just like to mention something called Accelerating Australia, which I also chair in Australia. This is an initiative, it's a consortium at the moment of 19 parties across the whole of Australia, including universities, biotechs, healthcare providers, and entrepreneurship training providers. And we're actually trying to do very much what Salvo was saying, and I'd love to chat to you afterwards about this. We're trying to get this translation happening in Australia, have entrepreneurship developed, enable people to translate their research from the laboratories to get them to patients and meeting those unmet needs. So thank you very much.
Great. Can we give Kevin a round of applause? So, clearly a very powerful technology, Kevin. If you kind of had to summarize, areas that you're most excited about with the bioluminescence technology in terms of kind of understanding signaling all the way from the receptor, down through intracellular signaling. What do you think, for an audience that's thinking about, well, how do I use this technology? What would you say are the applications that you think, the technology could be used for, but hasn't really, taken off yet?
Yeah, so this technology, it opens a Pandora's box in many ways because we always thought about receptor signaling as individual receptors. But if you now think there's 800 non-olfactory receptors, and you can put them in multiple combinations, we have an amazing opportunity. There are, particularly in the neuroscience field, but also in the endocrinology field as well, many combinations, and they could be where side effects are coming from. So we think of a lot of our pharmacology, a lot of our compounds, perhaps giving us side effect profiles, which means they're discarded. If we can understand the pharmacology at this level, and perhaps there are complexes involved, if we understand them better, we can address those side effects early in the pipeline and therefore have a much more viable product at the end.
Perfect. Thank you very much, Kevin. So a round of applause for Kevin. I'd like to ask Wensheng to come up. So Wensheng Wei is Associate Professor at Peking University, and he's a PI at Biopic, and also the Beijing Advanced Innovation Center for Genomics. So Wensheng trained with one of the greats of molecular biology, Stan Cohen, in Stanford, and his group really is today, one of the groups that's at the forefront of developing CRISPR-Cas9 technology for use in developing some novel high throughput functional genomics assays. And I'm going to let him kind of outline some of the ways in which his group are thinking about using the technology. Over to you.
All right. Thank you so much, Andy, for the kind introduction and invitation. So a little bit about myself. I got my PhD from Michigan State University and at Stanford for the postdoc training before I returned to China and start my own lab. And for the almost 10 years, actually just past 10 years. So for the past 6 or 7 years, the main focus of my lab is mainly on the technical part, dealing with genome editing technology, starting from very beginning, the basic technology, including TALEN and CRISPR, and also some of the repurposing using technology to do some imaging work. But the most of our research focus is on high throughput screening, and starting from doing the coding gene functional genomics, all the way to the non-coding, especially the link RNA functional genomics. And now we are working also on the 3D structure to mapping a special structure to link the structure with the function, as well as some special technology to make the function domain even the single critical amino acid, which is important for the function of the protein of interest. So basically, to conduct high-throughput CRISPR screening, there's a technical issue. Normally, we have to use a very low MOI to making the library. The reason is because we don't want to have more than one sgRNA entering, more than one viral particle carrying the sgRNA entering one cell, because that will complicate the issue. We have more than one sgRNA have misassociation. So at the same time, if we make a larger size library, like genome-wide, that will consume a lot of cells because of this very reason. So to dealing with this very problem, we recently developed a new technology which allows us to use a very high titer of virus, high MOI to do the experiment. Using the high titer of virus for infection based on the conventional CRISPR screening, so this is to replicate. The consistency will suffer a lot. Using our new technology, we will have a very consistent ranking for both replicates. In that way, we don't have to conduct experimental replication because we have an internal tracing system. So by doing that, we can achieve over 20-fold reduction on the workload. So this is especially important if we are dealing with a very limited amount of material. And as well as some of the special conditions, if we have to conduct in vivo screening, this would be extremely useful. So for the past couple of years, people have done a lot of CRISPR screening, mainly dealing with to associate function with the coding gene, which is basically protein coding gene. So the question is whether the protein is the only druggable targets. So for that reason, we are thinking and looking for something else beyond protein coding genes. So for the part of my talk, main part is really dealing with those non-coding RNAs. The reason is because all those protein coding genes, they only comprise of less than 3% on the whole chromosome region. So majority encoding many other things, including especially non-coding. In particular, the non-coding RNAs have over tens of thousands, basically at the same scale of number with the coding genes, but with a very limited amount of information regarding their particular function because of lacking of a specific high-throughput way to investigate. So we try to answer the very question to establish methodology to allow us to screen for the function of a link RNA to have a possibility to answer this question, whether link RNA essential for certain cancer viability may present a new category of therapeutic targets. So by doing that, we just published a paper in MBT last year by introduce a pair of sgRNA to introduce double cut to make a large deletion. Okay. The reason we could not use traditional CRISPR screening to study link RNA is because those non-coding, they are not making the protein, so they are very insensitive to the reading frame caused mutation. That's why we are trying to make a double deletion to make the high-throughput screening. So by doing that, we were able to identify a lot of candidate link RNA, which being negatively selected through the screening. In a sense, those link RNA, their deletion will cause cell death, okay, indicating they are essential for cell viability. And those particular essential link RNA, based on the geo annotation, we pretty surprisingly to find out their expression actually correlates very well with the cell malignancy. So from normal cell to a more metastatic stage, the expression level going up, following a very similar kind of pattern. This suggests those type of essential link RNA behave like an ONCON type of gene, whether they are indeed ONCON gene or present another category of druggable target. This remains to be determined. We were able to identify another category of genes whose deletion will make the cell grow even more faster, okay, replication or faster. Those type of genes, based on the RNA-seq data, we identify the loss expression or deletion of those type of link RNA will upregulate a lot of cancer-related genes or pathway, indicating this might be a new type of tumor suppressor gene. Again, their biological definition of whether they indeed belong to this such kind of category still remain to be determined. Okay, so we were able to using double cutting to make a library to establish the screening methodology, but they're still technically pretty challenging to introduce two sgRNA into one cell. To scale up, it's pretty challenging. So we're making another approach, allow us to really achieve a genome-wide link RNA library coverage. So using that, we were able to identify a lot more essential gene in this particular K562 cancer cell line, more than using a different technology, which is CRISPR, which is a suppression at the promoter region. We can validate for all validated 44 link RNA, we can confirm they are true positive. So this particular technology is by far the only genome-wide loss of function screening, allow us to have the capability to comprehensively and conduct genome-wide screening to study whatever biology we are interested in. So besides link RNA or other non-coding RNA, we're also interested in studying some special chromosome structure, okay? Try to link the particular structure where their potential function. So I'm going to go very quick on this, and this very study is using the paired gRNA, the introduced deletion. So by doing that, we were able to identify a number of so-called hubs in particular cancer cell lines and associate this particular structure with the cell proliferation or cell viability. So by identifying for the first time the functional hubs or hotspots, we were able to come with this realization that the disruption of hub formation which is uniquely essential for cell viability, might lead to new therapeutic intervention, the kind of a new kind of direction. So another kind of very straightforward application using paired gRNA library for screening is to try to identify those genetic interactions. Basically, this is particularly useful to study synthetic lethality pair, to try to identify the pair of genes, both mutation will lead to the cancer cell death. So this is a very important area, and two publications just recently in NBT and Nature Method to use this very method to do this kind of a screening. So because of a time limitation, I will go very quickly to the last part of our new technology development. So for any kind of screening, whether we study coding gene or non-coding, so next stage is to try to understand the mechanism to figure out if it's a protein, what is the binding domain for ligand, or what is a catalytic important critical amino acid. So those type of things is a very demanding and very urgent need if we have identified any novel component from a screening. So in terms of drug resistance, cancer drug resistance, oftentimes one of the popular type of mutation is a point mutation occurring in the drug targets. Okay, to identify those potential mutation which confer drug resistance is extremely important. So based on that, we developed new technology, basically allow us to decipher the drug resistance mechanism. We call this CRISPR. Okay, this is based on CRISPR saturation mutagenesis, but combined with a different kind of technology for the sequencing. And I'll just show very quickly the kind of thing we can do. So this is PSMB5 proteasome subunit, which is a cancer drug. These very proteins, there's a lot of non-point mutation which confer drug resistance and show in the star area. Using our technology, we are able to map all of the known single amino acids as well as some novel amino acids, and we can demonstrate the point mutation at this critical site will confer drug resistance. Okay, so this becomes such a powerful method. And another very exciting development out of the CRISPR strategy is we were able to, after the initial primary screening, able to identify all the single amino point mutation pattern. For example, we have PSMB5 and PLK1, two cancer drug targets, and for the top 10 single amino acid critical for the mutation will confer drug resistance, we have to identify different kind of pattern in this very comprehensive heat map. So for example, this very spot, there's a dominant mutation which can confer resistance. For some others, there's different kind of patterns. So this is in more details. As I said, for PSMB5, for this M104 spot, the methionine have to substitute into the eye, isoleucine, to confirm drug resistance. If the mutation occurs in into some other type of amino acids, that will not confer any kind of drug resistance. Similarly, C have to convert into lysine to confer resistance. And a very similar pattern we can also identify from PLK1. And this particular one, this is dominant pattern. So this type of thing gives us a lot of opportunity and very in a very depth to tell us all the detailed information, allow us to generate all possibility, all the point mutation possibility, to tell us all the knowledge, to allow us to have the knowledge to for the new drug development, and try to better understanding so-called drug resistant mechanism. So quickly summarize what I've been talking. We are among the first couple groups to establish the first CRISPR screening, and we have a new technology further accelerate to try to scale down the workload. And we were able to develop new technology to screening the linker RNA function, and the two technology have a different kind of scale set. And for the pgRNA, paired gRNA library, We can also using that to study something very unique and different. One thing is for functional connection with the city structure with the function. Another is the gene pair identification for the synthetic lethality. And lastly, we have the newly development technology to allow us to map the critical amino acids essential for cancer drug resistance. So with a series of technology, I founded a company less than 2 years ago, and we have some employees so far. And the thing we are conducting actually is providing some genome editing type of service and products. For example, we have to make more than 1,200 gene knockout cell line, which can provide to the antibody company for the golden standard to verify the quality of antibody. And we are also very interested to using the technology for the therapeutic development. So that's why we are very open to any kind of partnership or joint venture for drug resistance based on especially the functional genomics, the thing what I'm talking about today. So with that, I'm going to acknowledge my two groups, one from Peking University, another one is from Edging, the company we founded. And I'm open for any discussion afterwards and for any question if you have. Thank you.
Great. So, Wensheng, you've kind of described a whole array of different assays that kind of can inform us about target biology. And then the last kind of example you gave was this, quite powerful technology for kind of understanding, what kind of resistance mutations might occur in a drug target. So do you have a feeling for which of these assays are the most kind of compelling in terms of a company that would come to you and ask for you to do a service for them?
I will say for the general screening, whether it's working on coding gene screening or non-coding, it's really important to identify the potential new drug target, as well as understanding the late stage, to provide the biomarker for any kind of a new drug. Because some of the drugs, they fail because they didn't identify the proper patient pool. Because of lacking of companion diagnostic knowledge, this can be very well be provided by this kind of screening. But also, I think the CRISPR, the domain mapping technology is extremely useful, in my opinion, because that will give us a very clear idea what's the cause, what's the mechanism behind the drug resistance. So we can do new drug identification, or we can develop a new way to treat a certain cancer based on this very technology. So I think this could be extremely important for practical use too.
Thanks. Okay, so that brings our first session to an end.
Yeah, and we'll be breaking for coffee now. So coffee is served at the side of the room, and we will come back at 3:50.
Okay, thank you very much, everybody.